We're surrounded by what looks like total chaos. Stock prices, weather patterns, even the number of people in a coffee shop. But what if there's a hidden order to it all? Today, we're going to crack the code using some of the most essential tools in data science, probability distributions.
So that's the big question, right? How do we actually do it? How do we look at a world that seems to be full of random, uncertain data, from customer behavior to climate science, and find something predictable? Something we can actually use to give us an edge. Okay, so the world is full of uncertainty. We all know that. But here's the secret. Data science doesn't get rid of the randomness. Nope. It gives us a language to understand it and a set of tools to find predictable patterns right in the middle of all that noise. And that's exactly what we're going to dive into.
All right, so here's our game plan. We'll kick things off by framing the uncertainty problem itself. Then we'll learn the language of randomness, get to know the famous bell curve and its opposite, explore some tools for counting success and failure, and finally, we'll put it all together into your very own data science toolkit. First up, the uncertainty problem. Before we can even get to the answers, we've got to really appreciate the question, right? How do you turn what looks like pure chance into a powerful, useful insight?
Seriously, think about it for a second. Predicting the weather, analyzing the stock market, even just figuring out how many cashiers to have at the grocery store. They all seem like totally different puzzles. But here's the thing. Underneath it all, they are all built from the same basic stuff. Probability distributions. This is the secret language that makes sense of it all. So let's get into that language. In Section 2, we're decoding randomness. We're going to start with the absolute basic vocabulary you need to know to speak data.
Okay, first things first. All data pretty much falls into two big categories. On one side, you've got discrete variables. These are things you can count. Like when you roll a die, you can get a 1 or a 2, but you can't get a 2.5. It's distinct. Then, on the other side, you have continuous variables. These can be anything within a range. Think about temperature. It could be 70 degrees or 70.1 or 70.11. You get the idea. And look, this difference is everything. It's what tells you which tool to grab from your toolkit. So what is a probability distribution anyway? Well, in simple terms, it's just a way to map out how likely each different outcome is. It's like taking this giant messy pile of random data and sorting it all out so it forms a shape that reveals a clear pattern. It turns a jumble of numbers into a picture we can actually understand and use. All right, now we get to the fun part, the shapes themselves. In this next section, we're going to explore two of the most fundamental patterns you will ever see in data. We're talking the bell curve and its total opposite, uniformity. Let's start with the undisputed celebrity of the statistics world, the normal distribution. But you probably know it by its much more famous name, the bell curve. And there's a really good reason it's so famous. This elegant, symmetrical bell shape pops up absolutely everywhere. Seriously, people's heights, scores on a test, even tiny little measurement errors in a science lab. They all tend to clump around an average value. The further you get from that average, the fewer examples you find. It's perfectly symmetrical, with the mean, median, and mode all lined up right there in the center. Okay, lean in, because here is the secret code to the bell curve. You just have to remember three numbers, 68, 95, 99.7. That's it. This simple rule tells you that for any normal distribution, about 68% of your data falls within one step of the average. About 95% is within 2 steps, and almost everything, a whopping 99.7%, is within 3 steps. It's an incredibly powerful shortcut. It's like a data superpower. All right, now let's flip the script and look at a completely different shape, the uniform distribution. If the bell curve is all about things bunching up in the middle, this one's the exact opposite. Here, every single outcome has an equal shot, which gives us this very distinct, flat, rectangular shape. So where do you see this? Well, think about rolling a fair die. Every number from 1 to 6 has the exact same 1 in 6 chance of coming up. Same deal with flipping a coin. It's also the basis for things like lottery systems, or when a computer needs to generate truly random numbers for a simulation. Basically, if every outcome is just as likely as any other,
you're looking at a uniform distribution.
All right, time to add a couple more specialized tools to our kit. Section 4 is all about counting things. We're talking success, failure, and how often certain events happen. This quote just nails it perfectly for our next tool, the binomial distribution. It's designed for any situation that has only two possible outcomes. Success or failure, yes or no, win or lose. If you're counting the number of successes in a fixed number of trials, this is the tool you reach for. And what's really cool is how the shape of this distribution can change. As you can see on the left, the graph is skewed. That's what happens when success is way more or way less likely than failure. But check out the one on the right. When the odds are 50-50, like with a coin flip, it becomes perfectly symmetrical. And hey, it starts to look a lot like our old friend the bell curve, doesn't it?
Okay, so binomial is perfect for counting successes in a set number of attempts. But what if your question is a little different? What if you need to count how many times something happens over a continuous period, like in an hour, or over a certain area, like a square mile?
For that job, we need the Poisson distribution. And this thing is an absolute workhorse. It helps us model things like the number of customers who walk into a shop in an hour, or the number of car accidents on a specific highway per day, even the number of typos you might find on a single page of a book. The rule of thumb is simple. If you're counting events happening over an interval, you're probably thinking Poisson. So there you have it, 4 really powerful tools. For our final section, let's get them all organized into your personal data science toolkit. We're putting it all together so you know exactly what to use and when to use it. And here it is. This is your ultimate cheat sheet. Seriously, knowing which tool to grab is the most important skill here. So let's recap. If your data is continuous and it's all clustering around an average, you grab the normal distribution. If every possible outcome is equally likely, you go for uniform. Counting yes or no successes in a set number of tries, that's a job for binomial. And counting how many times an event happens over a stretch of time or space, that's Poisson, all the way. Look, these 4 distributions, they are the absolute foundation of any data scientist toolkit. They're the first, most powerful step you can take to go from a world that looks like random, messy uncertainty and transform it into a predictable pattern you can actually work with. I'm going to leave you with this thought from Sir Francis Galton, one of the pioneers of statistics. Now, he was actually talking about the bell curve when he said this, but honestly, his sense of awe applies to everything we've talked about. He called it a wonderful form of cosmic order. A beautiful, hidden pattern just waiting to be discovered inside the chaos. And that leaves just one question. What patterns will you find?